I'm Zor. Welcome to Unizor Education. Today's topic will be quadratic functions. Quadratic functions. The lecture has notes which are on the unizor.com website, so you can read the notes first or after my lecture, whatever. I would like to present quadratic functions not as just, okay, this is a piece of information which you have to remember. I would like to increase the complexity of the explanation about whatever quadratic functions are gradually from a simple case to a more complex case. So we will all be thinking about what exactly the quadratic function is and what's its properties, etc., etc., and we will derive this information rather than I just give it to you. So let's start with the simplest quadratic function. The simplest quadratic function is this. Y is equal to x squared. Now, it's basically a particular case of the most general quadratic function, which I can write like this. So this is the most general one, but we're not considering it right now. We are considering this function with p equals 1 and q and r equal to 0. So this is for later. Right now we're concentrating on the most simple one. Now, when we are talking about functions, we have to talk about, first of all, where it is defined, what's the domain, where it takes the value from, codomain, and what's its range. All right. Quadratic functions, as we will be discussing in this and some future maybe lectures, are always defined on a set of real numbers. Yes, quadratic function can be in theory considered for complex argument. Remember, the complex is something like a plus bi, where I squared is equal to minus 1. We are not considering complex numbers as arguments to quadratic functions. When we will be talking about quadratic equations, we will definitely consider complex solutions. But right now, when we're talking about quadratic functions, it's only functions defined on the real argument. So x is any real number. Now, why is it any real number? Because any real number can be multiplied by itself, which is square, and as a result, you will get, again, the real number, which means the domain for this function is all real numbers. Codomain is also real numbers, but now my question is, the range of this function, the values which it takes, does it cover an entire set of real numbers? Well, the answer is no, because positive and negative numbers squared would result in the positive number. So minus 2 squared is 4 and 2 squared is 4. You cannot get negative number by multiplying any real number by itself. So domain is all real numbers. Codomain, well, you can say that it's all real numbers, but the range where the function really takes values is only non-negative real numbers. 0, by the way, is a real value. If you put 0 here, you will get 0 as a result. So 0 and all positive, which means non-negative real numbers are the range. Okay, we've done that. Now, how about the correspondence between the domain where the function is defined, the arguments, and the range where the function takes values? In some cases, like for instance in case of a linear function, we have a one-to-one correspondence between domain and the range, because for every real number of a function, there is always the real number of the argument, which if substituted into this function gives the result. It's not the case with y equals to x squared. Why? Because you cannot talk about one-to-one correspondence if 2 will result in the value of function 4, and -2 also will result in the number 4. And any other pair of positive and negative numbers with the same absolute value will actually result in a similar situation. So it's not one-to-one correspondence between all the values from the domain and all the values from the range of the function. However, we can always restrict our function to a narrower domain. So what if I will consider this function y is equal to x squared only on the domain of non-negative numbers? Well, in this case, we do have a one-to-one correspondence, because for every so let's say it's a different function. I will use q is equal to p squared. P is an argument, q is a function. But I will consider this function only on this domain. Now, if I have any p, I will obviously get some value of q. But if I will get any q, then I can always have a square root of q, the arithmetic value of square root of q, the positive or equal to 0, the arithmetic value. And that will be an argument, the square of which, substituted into this function, will give the q. And if you remember, I'm always capable to take the square root of positive or equal to 0 number, because actually that's how real numbers were introduced. If you remember the lectures where I was explaining what are the real numbers, I was talking about certain shortcomings of rational numbers. Like, for instance, you cannot find a rational number, the square of which equal to 2. There is no rational number like that. So we have introduced real numbers to expand our universe of rational numbers to be able to find such a value p, the real number p, the square of which is equal to 2. So that's why I can always say that in the domain of non-negative real numbers, this function does establish a one-to-one correspondence between all the domain elements and the range elements, because the domain will be non-negative and the range will be non-negative. And for every domain, I can always, for every element of the domain, I can find one and only one element of the function. And obviously, for any value of the function, I can find one and only one element of the domain. And that's what established this one-to-one correspondence. Okay. Let's forget about this one-to-one correspondence and let's go back to our real numbers as the full scale, all the real numbers, as arguments to this function, as it is usually done, basically. So, what I can say about this function, that this function is even. Now, if you remember, what is even function? Function is called even if for any x, if for any x from the domain, for any argument, I can say that the value of the function at certain value of the argument is the same as the value of this function for the value of the argument being negative to this one. If the values are the same, then the function is called even. Now, is this function even? Well, obviously yes, because we have already stated that positive number being squared and the corresponding negative number with the same absolute value with a different sign being squared actually results in the same thing. So x squared is equal to minus x squared. Interesting detail. I mean, I was just explaining this, but can we prove it? Well, that's maybe a little bit less trivial, but let's just think about what is minus x. Minus x can always be represented as minus 1 multiplied by x, right? I mean, that's from the definition of multiplication, negative numbers, etc., etc. Now, being squared, it's minus 1 times minus 1 times x. That's what it is. Square means you multiply it by itself. Now, I'm sorry. All right. Now, okay, hope they finish. Multiplication is commutative, which means okay, this is from the commutator. Well, we have a construction running. Anyway, now if you will multiply sequentially, minus 1 times minus 1 gives you 1 times x. X times x squared is x squared, so this is equal to x squared. So this is actually a proof. I'm using the definition of what is minus x, and I'm using the commutative property of multiplication. So I've proved that this function is even, because x squared is the same as minus x squared. Yeah, this is a trivial proof, but look, everything should be logically solid. So if you are stating something, you have to be prepared to prove your point. So I proved my point. This is an even function. Now, since this function is even, then its graph is symmetrical relative to the y-axis. Now, I will start working with graph right now. I will explain how the graph should go. But whatever I will use as my logic to draw the graph for the positive x, no, negative rather, x, then I will use the symmetry and reflect it relatively to the y-axis to get the other part of the graph. So I will draw the graph of this function only for non-negative x. And then by symmetry I will extend it to the negative part. Alright, so let's talk about how this particular graph looks like. Well, first of all, we can start from the point where argument is equal to 0, and the function obviously is equal to 0 as well. So the graph starts here, and then we extend it to the right, increasing the argument, and then I will reflect it by symmetry relative to the y-axis. Alright, so first of all what we can say is that the graph should go upwards, because for every greater value of x, the value of y is also greater. If the number is multiplied by itself, which is x squared, the greater the number we take, the greater the result will be. So, I would like to stop at point 1, where the function is obviously also equal to 1. So we have 2 points. We have point 0, 0, and we have point 1, 1. These 2 points definitely belong to the graph. Just out of curiosity, consider this function. Now, you know this is the straight line, and it also intersects. It also crosses these two these 2 points, 0, 0, and 1, 1. Now, how does this graph look relative to this one? Let's think about it. If you multiply the value which is less than 1 by itself, which is also less than 1, you will make it smaller, right? For instance, 1/2 times 1/2 is equal to 1/4. So the result is smaller than the argument. So if I am between 0 and 1 with my argument, the value of my function would be smaller than the argument. So in this function, the value of the function is equal to the value of the argument. This is the argument, and this is the function. Now this is smaller, so the graph should be below this. So no matter where I am in this interval from 0 to 1, the value of my function would be smaller than the argument. So the function will go under this particular line, y is equal to x. However, at this point, it intersects it, because the value of the function is exactly the same. So I'm assuming, basically, that the function will probably go something like this. Now, after x equals to 1, if you increase the argument, so you're multiplying the number which is greater than 1 by itself, which is greater than 1, which is increasing. So the function will be, the value of the function will be greater than the value of the argument. If the value of the argument is 1.5, for instance, squared, it would be what? 2.25, right? So I'm increasing, the value of the function is greater than the value of the argument. So it will be, so the graph will be above this, this line. So it will be something like this. So I am assuming from purely qualitative properties that the graph will probably look like this. Now, let me put a little bit more logic into this particular shape. The next consideration is the steepness of this graph. Now, what is a steepness of the graph? Well, I can measure the steepness the following way. I take 2 points, let's say x1 and x2. And then I take the value of the function, which is y1 and y2. And I measure this particular angle. So how much function has increased, which is y2 minus y1, relative to how much argument has increased. What I'm saying is that the steepness of the function can be measured by this ratio, how much function has increased versus how much argument has increased. Now, if function is linear, y is equal to x, we know that the function and argument are exactly the same, right? Which means that this particular ratio for this function will always be 1. Because y2 is equal to x2 and y1 is equal to x1, so their ratio is equal to 1. So the function, which is a straight line, y is equal to x, has a steepness of 1 always. Now, how about this function? Well, that's not the same, obviously. If you will take y2 minus y1, which is x2 squared minus x1 squared divided by x2 minus x1. As we know, this is equal to x1 plus x2. For those who don't believe it, can multiply this by this and you will get this. So this is actually not a constant like in this particular case. It's a variable which depends on x1 and x2. Now, what I'm also trying to establish is a local steepness. Now, local steepness means when x1 and x2 are very close to each other. So in this case, when these two values are close to each other, it's a good measure of the steepness at the point of argument x1. If x2 is very close to x1, then this particular thing would be very much a local characteristic of the curve. And now we see, okay, so this is approximately equal to 2x1 if x2 and x1 are very close to each other. Now, what I'm actually saying is that this thing is increasing with increase of the argument. So if x1 is shifting to the right, increasing basically, then the local steepness is actually increasing as well. It's equal to double x1, x2. So the steepness must increase, which means that the curve goes steeper and steeper and steeper as we are increasing argument. That's very important, actually. Now, what I did right now is I have introduced basically the beginning of analysis where you have the derivative basically from the function. I'm not using the word derivative, I'm not using the limit theory, etc., etc. I'm just trying to explain it in more elementary, from the more elementary standpoint. But basically the steepness is something which is, in this particular case, related to, okay, somebody's calling me. Okay. So this is basically how the steepness can be measured. And as we see, the steepness is increasing, which means the curve goes steeper and steeper to the right. Now, obviously, using the symmetry, because this function is even, I can say that the continuation of this would be symmetrical relative to the y-axis. So the complete graph of this function, x squared, looks like this. And it's called parabola. The word which we probably all know about, but this is the beginning where the parabola actually started. This is the function, the main function, and that's how parabola has started. All right, so now we are ready to complicate the concept of function, and we will gradually try to increase the complexity of this function from the elementary quadratic function to basically ultimately to the general form, and that will be a subject of the next lecture. Thank you and good luck. Hi, I'm Zor. Welcome to Unizor Education. This is yet another lecture which is dedicated to quadratic functions. In this particular case, it's a kind of a practical exercise. I have a set of 6 different quadratic functions which I would like to basically analyze. Analysis of a function is very easily accomplished by basically building its graph. So I would probably concentrate mostly on how to build the graph of these quadratic functions, and in particular, where is the vertex of the parabola? We know it's parabola, right? So where is the vertex of the parabola? What's the direction of its 2 branches, 2 horns, as I called them once? Upwards or downwards, and what's the steepness of this particular of these particular branches. This is basically how you investigate the behavior of the function. Now, all of these functions are represented in their general format. Now, general format is px squared plus qx plus r, where p, q, and r are real numbers, coefficients. Now, I cannot really, just looking at this particular form of the function, tell how the graph actually looks like. But I can if the function is represented in this format. Now, this is a full square format of the function. Now, how does this parabola look? But that's very easy. You start from the regular parabola, which is something like this. Y is equal to x squared. You shift it to the left by b. If b is positive, it's to the left. If b is negative, it would be to the right by the absolute value of b. But in any case, you shift it to the left by b, so it will be something like this. If this point is minus b. And then you multiply this function by a, and that means if a is positive, the branches remain pointing upwards. If a is negative, it will be changed to pointing downwards. If a is greater than 1, the steepness would be greater, let's say something like this. If a is less than 1 in absolute value, the steepness would be less, something like this. And then finally you shift it up by c. That would be your new vertex. So I know how to build the graph of this function, whatever coefficients a, b, and c are. So my most important problem is to convert the function from this representation to this representation. Now, last lecture, which was about this generic format of the function, I actually converted this into this in general variables a, b, and c, and p, q, and r. Now, I actually wrote a couple of formulas here, which basically relate this p, q, and r to the new coefficients a, b, and c. From this, we can always derive a, b, and c. Obviously, p is not equal to 0. Now, and the formulas are, I will just write it down. A is equal to p, b is equal to q divided by 2p, and c is equal to r minus q squared divided by 4p. Now, these are formulas, and I can actually use these formulas to convert this into this in any case which I have. Now, before doing this, I would like to say that I don't want to do it. And I don't really want I don't want to encourage you to do it this way. Why? Because you have to remember these formulas. I myself don't remember it, that's why I put it here as a kind of a reference point. And I don't think it's the right approach. I mean, we are here not to achieve certain, transformation, but to get smart about how to do this. So these logical and analytical skills would help us to do something else. The development of these analytical skills is the most important part, which we would like actually to accomplish here. So that's why I don't want to use these formulas. And I will do it differently. So to demonstrate how you can do it without knowing these formulas. However, I will do the first one just for fun. I will do using these formulas, and we will see whether it will give me the same result if I will do it more analytically, more logically, if you wish. So, in the first case, I have the function y is equal to x squared plus x plus 1. Now, what does it mean? It means p is equal to 1, right? Q is equal to 1, and r is equal to 1. Now, using these formulas, I will have a is equal to 1, b is equal to q divided by 2p, 1 divided by 2, so it's 1/2. And c would be equal to r, which is 1, minus 1/4, which is 3/4. So I can say that in this particular case, I can rewrite this function as y is equal to 1 times x plus b, which is 1/2, square, plus c, plus 3/4. Okay, now, let's check it out. I don't really need this anymore. I don't need this formula because I don't want to use it anymore. I will do something else. And let's check this out. Well, x plus 1/2 square, so it's x squared plus 2 times x times 1/2. 2 times 1/2 is 1 times x, so it's x. Plus 1/2 square is 1/4, and plus 3/4. And this is 1. So it's exactly the same with this. So this is actually a correct representation of our generic function in the generic format, and this is the correct representation in the full square format. Now, I know how to build the graph of this function. This is the regular parabola shifted to the left by 1/2 and up by 3/4. So it would be something like this. This is minus 1/2, and this is 3/4. This would be the vertex of my parabola, and it will have the same direction and steepness of the branches as the regular y is equal to x squared parabola. So that's my analysis, but I was using these formulas which I don't want to remember, and I don't want actually you to remember. So how can I come up with the same result like this one using, some more human-like, natural, analytical abilities which everybody hopefully has? Well, here is the point. What's most important right now is to find this particular coefficient. Why? Because this we can always adjust, whatever will be left. Now, let's just think about it. Now, x squared is the result of, obviously, squaring of the x. And then we have a double product. So if you have x plus b squared, this is x squared plus 2bx plus b squared, right? Everybody knows this formula. And if you know, you can always multiply it yourself. So how can I find b such that 2bx would be equal to whatever my element with x to the first degree is? Well, obviously, if this coefficient is 1 in this particular case, then this b should be half of it, because we double it, right? So if I have this, it means b must be equal to 1/2. So after doubling, I will have exactly x. So this is the first and most important part. So I know that it should be x plus 1/2 squared. Now let's just think about it. X plus 1/2 squared will give me x squared. It will give me 2 times x times 1/2, which is x, and it will always it will give me something else, which is 1/4. This is a free member, 1/4, but I need 1, so I have to compensate. I have to add another 3/4 to get to the 1. So this is the logic, and I will repeat this logic another 5 times, so you will kind of familiarize yourself better. Now, the only thing is a small nuance, which does not really exist in this case. The coefficient in this case is 1 with x squared, right? Now, what if it's not 1? Well, obviously we have to really factor it out, because again, that is something which is very easily to accomplish, and then the rest will be the rest will have a coefficient of 1 with x squared, and I will use this approach. So let me demonstrate it for the second example. Now I'm not using the formula, I'm just using the second example straight, and I'll just demonstrate the logic. So you have y is equal to 2x squared plus x plus 1. So the first step in converging this into full square mode is to factor out the coefficient at x squared. So it's equal to 2 times x squared plus 1/2 x plus 1/2, right? So now I have x squared here. Now what I'm thinking is I have to find out such a b that x plus b squared would have the first members like this. Now, what is it? Obviously b should be equal to 1/4, because then 2xb would be equal to 2x and 1/4, so it would be 2 and 1/4, so it's 1/2. That's exactly what I mean. So next is, I should say, this is supposed to be equal to x plus 1/4 squared. Now, that would satisfy x squared, and it would satisfy 1/2 x. Now, 1/4 squared would be 1/16, but I need 1/2. So I have to add whatever I need to add to 1/16 to get 1/2. 1/2 is 8/16. I have 1/16, so I have to add 7/16. Right? Basically, that's almost it. The only thing which remains actually to do is multiply separately by these two things using the distributive law. So it's 2 times x plus 1/4 squared plus 2 times 7/16 is 7/8. So this is my answer. This is my full square for this particular thing. Just in case, let me check if I'm right. Okay, equals to 2 times x squared plus 2 times x times 1/4, so it's 1/2 x, plus 1/4 square, which is 1/16, plus 7/8. Okay, multiply 2 times x squared, it's 2x squared, plus 2 times 1/2 x is x, 2 times 1/16 is 1/8, plus 7/8. 1/8 and 7/8 is 1, so everything is fine. So this is just checking, but most important is that I have transformed or converted my original general representation of quadratic function into full square. And now I can say very definitively how this particular graph looks like. So you have to shift my x squared, y is equal to x squared, to -4, so -1/4, so it's this way. So then the parabola should be multiplied by 2, which means it should be 2 times steeper, so it's something like this. And then shift it upwards by 7/8. So this would be the new vertex, and that's how it goes. So this is my graph, this is how parabola goes. It's twice as steep as the regular y is equal to x squared, and its vertex has the x coordinate -1/4 and y coordinate 7/8. That's the end of this particular analysis. So full square is the purpose of all these transformations, and I was trying to do it not using any kind of a formula, but just some kind of a logical transformations which led me to this particular case. Now next one, 3x squared plus 2x plus 5. Again, the first step, factor out the coefficient at x squared. So it's 3 times x squared plus 2/3 x plus 5/3. Second, how can I get this? Well, it's x plus how much to get 2/3 x? Well, this is supposed to be double x times this b, whatever the b is supposed to be, and obviously b is supposed to be 1/3, right? Because if I will do this, it will be x squared plus 2 times x times 1/3, which is 2/3 x. Now, I have 1/9 squared. I need 5/3. 1/9, and this is 15/9. So I need 14/9 to add. That's it. 1/9 plus 14/9 would be 15/9. Factor 3, 5/3. Yes, seems to be okay. Now, or I can rewrite it as 3 times x plus 1/3 squared plus 3 times 14/9 is 14/3. So this is my full square. And now I can say that this is the regular parabola y is equal to x squared. Then it should be shifted to the left by 1/3, made 3 times steeper, and then shifted up by 14/3. Just in case, let me check that I'm right. So it's 3 times x squared plus 2 times x times 1/3, so it's 2/3 x plus 1/9 plus 14/3. So it's 3x squared plus 3 times 2/3, it's 2x. 3 times 1/9 is 1/3 plus 14/3. So it's 15/3, which is 5. Yeah, I'm right. So checking is fine. All right, so that's it for this particular example. So let me just continue doing exactly the same thing. After a few more, we will all be very comfortable with this particular transformation. Y is equal to minus 4x squared plus x minus 1. Okay, equals minus 4 outside, factor out. What's left? X squared. This is minus 4, this is plus, so it would be minus 1/4 x and plus 1/4, right? Minus 4 times minus 1/4 would be 1. Minus 4 times plus 1/4 would be minus 1. Equals minus 4. Now, what is it? It's x plus b squared, right? Now, x squared. Now, we will have 2xb, and we will have to have minus 1/4. So what is b? Well, b should be equal to minus 1/8, right? 2 times x times minus 1/8 would be minus 1/4. Fine. Now, the free member would be 1/64, and we need 1/4. So 1/4 is 16/64, so I need another 15/64 to get to, am I right? So x squared minus 1/4 x plus 1/64 plus another 15/64, so it's 16/64, which is 1/4. Seems to be okay. Now, what is this particular graph? All right. First, it's shifted by, well, minus 1/8 to the left, which is actually plus 1/8, right? So this is 1/8. That's my vertex. Now, then, by the way, it probably would be easier if I will open these parentheses. So it will be minus 4x minus 1/8 square plus, actually minus 4 and 15/64 is 15/16, minus 15/16. Okay, that's the right thing. Well, just in case, let me check. It's minus 4x squared, okay. Then 2 times x times minus 1/8 is minus 1/4 x times minus 4 is x. And this is 1/64 times minus 4, it's 4/64, which is minus 1/16 and 15/16, so it's minus 1. Yeah, seems to be fine. Now, this graph is, again, as I was saying, it's shifted by 1/8 to the right in this case, because this is negative. Then the parabola should be directed with its branches, with its horns downwards, because this is a minus sign, and it should be 4 times steeper than the regular parabola. So it's something like this. Very, very steep, goes down. And then it should be minus 15/16, so it should be brought down So this is the parabola which I'm looking for. So the horns are looking down because this coefficient is negative, and this is the original coefficient. And it's very steeply goes down because the coefficient is 4 here. And then 1/8 and minus 15/16 is basically where the vertex is located. All right? Okay, so that's as much as we need for this particular case. Okay, next, y equals minus 3x squared plus 6x plus 4. Okay, same thing. The first step is factor out minus 3. Now we have x squared minus 2x minus 4/3 equals minus 3x squared plus 6x and plus 4/3. Okay, seems to be fine. All right, now, how to convert this into full square? Minus 3, so it's x. What should it be to get minus 2? Well, obviously minus 1 squared, right? It will be x squared minus 2x plus 1. Now, we have plus 1 here, but we do need minus 4/3, which means we have to subtract 7/3, right? So it should be 1, which is 3/3, minus 7/3 would be minus 4/3. That's what it is. Okay. Now, just to make it a little easier, it would be this. Plus 7. Right? Let me check. Minus 3x squared. This is minus 2x, so it's plus 6x. Now this is plus 1. Times minus 3, it's minus 3, plus 7 is 4. Correct. Now, how to draw this particular graph? Well, again, obviously it's 1 to the right, then direct the parabola downwards 3 times steeper, and then raise it up by 7. So it would be something like this. This is 7, this is 1, and parabola is downwards 3 times steeper than original y is equal to x squared. Okay, done. Okay, and I have the last one. Y is equal to minus 2x squared minus 2x minus 3. Okay, I'm sure you are very proficient by now with the technique. Factor out minus 2. We have x squared plus x plus 3 second, right? Equals minus 2 x squared plus x would be x plus 1/2 squared, right? It will give me x squared plus 2 times x times 1/2, which is x, and it will give me 1/4. Now this is 1/4, but I need 3/4. I need 3 seconds. So I have to add, this is 6/4. I have 1/4, so I have to add 5/4. Correct? X squared plus 2x and 1/2, so it's x, plus 1/4 and 5/4, it's 6/4, which is 3 seconds. That's fine. Or minus 2x plus 1/2 squared. Minus 2 times 5/4 would be minus 5 seconds. Right? Which means my parabola would be with the vertex minus 1/2 and minus 5 seconds. So it would be something like this. Minus 1/2 and minus 5 seconds. That's the vertex. The horns will be downwards because this is the minus sign, and the steepness would be twice as big as the steepness of the regular parabola. Well, that's the end of it. Basically, my purpose was to basically encourage you not to remember the formula, which you will probably forget anyway, but to try to logically approach. What we need is a full square. How can I accomplish this transformation to a full square? Well, first of all, this definitely prevents me from doing it, in a simple way. So let's just factor it out. That's the first step. Now I have the function which has 1 at the x, which means we should convert it into x plus something squared. And all we need to do is just to find this something in such a way that it will give me the coefficient with x to the first degree. In this case, for instance, it's 1/2. And then I see what my free member is supposed to be, what I have here, so how much I have to add or subtract to get to this. So this is the logical kind of a set of conclusions which you can make, set of steps which you can make to get the result without knowing any formula. And that's personally, I prefer this way because it will develop your ability to find the way in a new situation which you are not familiar with. Nobody gives you the formula to solve some real life problems. You have to basically come up with a way to solve it just on your own without the help of anybody. So this is just a simple example how you can use your own logic to accomplish this without knowing any additional formulas or anything like that. That's it for now. I do suggest you to do some exercises yourself. You can do exactly the same exercises which I did. The notes for this particular lecture are on unizor.com. And, well, good luck. Thank you. Hi, I'm Zor. Welcome to Unizor Education. Today's topic will be a couple of very small and very simple problems in the area of quadratic equations. Now, why these problems have to be addressed? First of all, there are some formulas which we touched during the lecture, the formulas for solutions of any quadratic equation. So why do we need problems? Just have the formula and basically substitute all the coefficients in the formula and you got the solutions. Well, yes, obviously. However, there are some reasons which really are much more important in this particular case. First of all, you can forget the formula, and all of a sudden you're facing with necessity to solve some quadratic equation and you forgot the formula. Well, that's not such a big deal, because you always have to remember how the whole formula was derived, and that's exactly why I want to solve a couple of problems, because the way how I will solve these problems is exactly the way how we derived the formula during the lecture. So it's easy to forget the formula. However, the approach you probably should always keep in mind, and again, in case you forgot the formula, you can always use this approach. At the same time, it's still useful to approach certain problems not from the formula basis, but just from the logical thinking. How would you address this particular problem if you don't know any formulas? So it's kind of a teaching problems, I would say, illustrational for the approach we used during the derivation of the formula itself. So I have two different equations here. And first of all, I would like to say that we are going to solve these equations in the area of real numbers. For complex numbers, we will have different set of problems. So number one, the domain is real numbers. Number two, I have different equations here. I have prepared three different equations. One will have two different solutions, another will have only one, and the third one will have none. But we will come to this gradually as it comes. So, number one is 2x squared minus 5x minus 3 equals to 0. So, I don't know any formulas. I would like to derive some solutions of this particular equation purely logically, more or less the same way as I derived in general case with general coefficients during the lecture. And that's exactly what I would like you to try. The approach which I will use, I will try to represent this as a square of something equal to something. For instance, basically x minus a, for instance, square equals to b. If I will be able to represent it in this particular form, then I can always derive x minus v, just square root of b, and then x. So this is also a quadratic equation. So if I will be able to derive from this with certain a and b, then my solution will be much easier. So that's the general approach. Simplify your equation to a form which is easily to solve. In this case, in the case of quadratic equation, this is basically the most simple and easily solvable type of quadratic equation. So you have to transform this into this, and then the problem will be almost solved. So that's the approach. I would like you to think about this, press the pause button, try to do it yourself, and I will basically do exactly this with the board right now. So I would like to have something like x minus a squared. Well, first of all, the coefficient with x squared is 1, and this is not. This is 2 in this particular case. So to represent this in this form, first of all, I have to divide everything by this coefficient with x squared to have it 1. Okay, so my first transformation will be, I will divide the whole equation, which is invariant transformation, by 2, and as a result I will have x squared minus 5 second x minus 3 second equals to 0. So this is invariant transformation. I divided both sides of the equation by 2. No solutions are lost or gained. Everything is fine. So x squared I already have, right? Now, if this is x squared, then this is obviously this, and then I will worry about all this, all the free coefficients without any unknown variables x. So, if minus 5 second is minus 2a, what does it mean? Well, it means that a is equal to, I multiply both sides by minus 1, that's invariant transformation, and then divide by 2. So it's 5/4. So I've got my a. Now, if I will change this into this, I subtract b from both sides, so I will transfer b to the left and put it equal to 0. Then obviously, a squared minus b is minus 3 seconds, right? Now, I know that a is 5/4, so what's the b? Well, if a squared minus b is minus 3 seconds, and a is 5/4, then obviously I will have 5/4 squared, which is 25/16, minus b is equal to minus 3 seconds. So what's the b out of it? Well, multiply everything by 16, so we will have 25 minus 16b equals to minus, that would be 24. So 16b, I add 16b to both sides, so 16 will go on the right, and then I will add 24 to both sides. 24 will go on the left, so we'll have 25 plus 24, 49, equals to 16b. So b is equal to 49/16. So, as you see, we have transformed our equation, original equation, first to this form, and then using these a and b, we transform it into this form. So I can say that my equation right now looks like x minus a is 5/4, square, equals to b, which is 49/16. This and this are exactly the same. If somebody wants to make sure that that's really the case, let's just think about this. This is x minus 5 second x plus 25/16. This is 49/16. So if 25 sixteenths and 49 sixteenths, that's 49 minus 25, 24. So it's minus 24 sixteenths reduced by 8, 3 seconds. Yes, that's exactly what it is. We did not make any mistakes. All right, so original equation we have reduced to this form, which is very easy to solve, because now we can use the square root for both sides. This is not an invariant transformation, but we will be very careful. And we will use the absolute value of x minus 5/4. The positive part of it is equal to square root of 49 sixteenths is 7/4, obviously, right? Because 7 squared is 49, 4 squared is 16. Great. So if this is a final equation, it means that either x minus 5/4 is equal to 7/4. That's one solution. And another solution is x minus 5/4 is equal to minus 7/4. That's what absolute value means. So the positive, well, from this x is equal to 5/4. We add 5/4 to both sides. We will have 12/4 reduced by 4, that's 3. Now, 5/4 on the right side minus 7, it will be 2/4. So it will be 1/2, minus 1/2. Is that right? Well, just in case, let's check. X is equal to 3, square will be 9, times 2 will be 18, minus 5 times 3, 15. 18 minus 15 is 3, minus 3, 0. Good enough. Minus 1/2. Square will be 1/4, so it will be 2/4, which is 1/2. Minus 5/2. Now 5/2 is 1/2 minus 5/2 is minus 4/2. No, minus, so I think I made a mistake somewhere. Did I? 1/2, it's 1/4. All right, let's do it this way. 2 times 1/4 minus, that's plus 5/2 minus 3. Minus 3. Now, plus because minus 5 and minus 1/2, it will be plus 5. Okay, now this is 2/4, which is 1/2, plus 2/2 minus 3. This is 6/2 minus 3, which is 3 minus 3, 0. Everything is fine. Okay, so checking is okay. Both are solutions. And as you see, using this transformation into this form allows us to very easily solve the problem. Now we will continue doing exactly the same thing with the other couple of problems which I have. Okay, next problem. Next problem is this: 4x squared plus 12x plus 9 equals to 0. And again, my purpose is to reduce it to the form x minus a squared equals b. Let's see what happens. Well, again, first of all, 4 really stands in the way, because I would like that to be x squared minus 2ax plus a squared minus b equals to 0. You understand I subtracted b from both sides, opened the parentheses and subtracted b. And now 4 actually stands in the way, so I have to divide the whole equation by 4. which is invariant transformation, no problems with that. And that would be x squared plus 12 over 4, that's 3x plus 9/4. So, my x squared matches this one. So, what should be my a? If 2 minus 2a is equal to 3, so my a is equal to minus 3 seconds, right? Now, and a squared minus b should be 9/4. Considering a is 3 seconds, a squared is a squared minus b is 3 seconds square will be 9/4 minus b, and that should be equal to 9/4. So b is equal to 0 from here. So my equation actually becomes b is equal to 0 and a is equal to minus 3 seconds. X minus 3 over 2, it will be plus 3 over 2 square, is equal to b, which is 0. Well, let's check just in case that this is the same as this. X squared plus 2 times x times 3 over 2, that's 3x. 3x plus the square of this one, which is 9/4. Everything is great. So, what's interesting about this particular example, this particular problem, is that on the right I have 0. When I use the square root in both cases, I will have an absolute value of x plus 3 over 2 is equal to 0. Now, if absolute value of something is equal to 0, it's not like positive or minus or negative. There is only one 0. Last time we had something like, I don't remember, 7 over 2 or something like this. So it was plus 7 over 2 and minus 7 over 2. In this case, 0 plus 0 or minus 0 is exactly the same thing. So this is example when both solutions, I use the word both because usually quadratic equations have 2 solutions. Both solutions are the same, so it's a double solution, so to speak. And solution is obviously x equals to minus 3 over 2 to make it 0. Again, let's check it out just in case. Um, 3 over 2 square will be 9 over 4 times 4 minus 12 times 3, it's 36 over 2 plus 9. Now this is 9. This is minus 36 over 2, 18, and plus 9, 0. Everything is fine. Okay? So that's an example of an equation which has only one solution. Well, we use the term double solution if you wish, but anyway, it's only one number. Okay, that's example number 3. And number 4, sorry, that was number 2, and this is number 3. Okay, the last one. 3x squared minus 18x plus 30 equals to 0. Good moment to press the pause button and do it yourself right now. Now, I will do exactly the same thing as before. I want to transform it into this particular form. Or, if you wish, x squared minus 2ax plus x squared minus b is equal to 0. That's the form I would like to transform it for. into. Okay, now this is x squared, this is 3x squared, so I divide everything by 3, that's number 1 obviously, so I have x squared minus 6x plus 10 equals 0. Great. Now, if minus 2x is minus 6x, then a is equal to 3, right? A is equal to 3. Minus 2 times 3 times x, that's exactly mine. Now, so a squared minus b is supposed to be 10, right? Now, a is 3, so it's 9, minus b equals 10. From which b is equal to minus 1. And that's very important. b is equal to minus 1. You see, b is on the right. On the left, we have a square of something, of a real number. Don't forget, we're solving in the real numbers right now. The domain of the solutions is the set of all real numbers. Obviously, no real number square will give minus 1. That's the complex numbers where we will have the number I, which will give this. But that's not what we're considering right now. Right now, we're talking only about real numbers. There is no real number square of which is equal to minus 1. So what does it mean? It means there is no solution. So among the real numbers, this particular equation has no solutions. And that's the final point which I wanted to make with this problem number 1, which is actually 3 different little exercises. And again, the most important part so far was to transform our original equation into this form, which is very easily solvable just because we can have the square root of both sides, if possible, if it's not negative on the right. Okay, that basically concludes the algebraic part of these 3 equations. Now I would like to illustrate everything geometrically. Now, if I have an equation, then whatever is on the left, which is a polynomial of the 2nd degree, power of 2, it's represented by some kind of parabola. Now, the horns of this parabola are directed either upward or downward, depending on the coefficient. If I have something like ax squared plus bx plus c is equal to 0. If this is my original equation, then this coefficient determines what exactly the direction of the horns of the parabola are. If it's positive, then it's upward. If it's negative, it's downwards. So that's number 1. Number 2, solutions to this equation is when this parabola is crossing the y equals 0 axis, which is this horizontal axis. So this parabola has 2 solutions. This parabola has no solutions because it doesn't cross the x-axis. And this parabola, which just touches this particular x-axis, has one solution which can be called double. So my original 3 equations which I had are actually illustrations to all these 3 cases. One case when parabola doesn't touch it, another is when there are 2 solutions, and yet another one when there is only one solution, but it's doubled. Now, let's just make it more concrete in each of those cases. So I will try to draw a graph, and we will see how it actually illustrates. So again, let's start from the beginning. 2x squared minus 5x minus 3 is equal to 0. I divided this thing by 2. X squared minus 5/2x minus 3 is equal to 0. And represented this as x minus 5/4 square, right? Because that would gives me 5/2x. X squared minus 5/2x. And then I have 25/16. So I have to subtract 25/16 and minus 3. And that would be my equation. So just let me combine these together. 3 is 25/16 and minus 3. So what were the roots of that? I don't remember. Is that right? 16. I thought it was plus. Let me just check it again. So I have x minus a squared is equal to b, right? So it's x squared minus 2ax plus a squared minus b is equal to 0. Okay, so this is covered by this. So a is equal to 5/4. So 25/16. Here it is. Minus b is equal to 0. Is equal to minus 3. Is equal to minus 3. Right? Minus 3. So b is equal to b goes to the right, 3 goes to the left. It's 48 minus 25/16. Am I right? Something is wrong. No, plus. Plus is no good neither. Is it 5/4? Let me check. 5. Oh, I know why. That's my mistake. It's not 3. It's 3 seconds. I divided by 2. See, that's my mistake. Okay, fine. So let's just change this a little bit. I see it's some unusual numbers which I didn't really plan for. Okay, now it's different. So now it's x minus 5/4 squared plus, well, actually minus 25/16, because this is plus 25/16 if I open the parentheses, and minus 3 seconds is equal to 0. Okay, now that's better, because now this is, instead of 3 seconds, I will multiply by 8, it will be 24/16, right? Now minus 25 and minus 24 sixteenths is 49 sixteenths. So change this to minus 49 sixteenths. Now that's familiar number. I remember that. Okay, now I can draw a graph of this particular polynomial. Now, if you remember, if I take the graph of function y is equal to x squared, that would be a parabola which goes like this. Almost perfect. Now, next is, let's draw the graph x minus 5/4 squared. Now, if you remember what happens with the graph if I substitute instead of x, x minus something, well, the whole graph shifts to the right by this something. For obvious reasons, so in this case, if this is 5/4, the parabola will be like this. New parabola. Because for the value of x is equal to 5/4, this graph is exactly the same as this one when x is equal to 0. And for the x is equal to 5/4 plus anything, it's the same as this graph when x is equal to that anything. So the whole thing is actually shifted to the right. This graph is shifted by 5/4 to the right from the original y is equal to x squared. So that's covering, we were talking about this part. Now we have to subtract something from the graph. Now subtract means the whole graph shifts down by, in this case, since it's minus, it's down, so it's 49 sixteenths. So if this is minus 49 sixteenths, the whole graph will shift down to this position, and still its horns will be upwards. And wherever the roots of this equation are, and the roots are, let's do it again, it's x minus 5/4 absolute value is equal to square root of, which is 7/4. Now, which means that x minus 5/4 is equal to plus or minus 7/4. If it's plus, then it will be 12/4, it will be x is equal to 3. And if it's minus, it will be minus 1/2. So this point is minus 1/2, and this point is 3. Well, the scale is obviously not very good, but in any case, this is the final parabola, and crossing of this parabola with the x-axis, which is 3 and minus 1/2, are exactly the solutions. So this is a graphical representation of the same thing. Now let's continue with the two other examples. Example number 2. I hope I will not make an arithmetic mistake with number 2. So we have 4x squared minus plus 12x plus 9 is equal to 0. So first I divided it by 4, so it's x squared plus 3x plus 9/4 is equal to 0. Now this is x plus 3/2 squared. Just to get 3 here, x squared plus x times 3/2 times 2, that's 3x. And so this is already 9/4. So basically my 9/4 is already covered. That's the same thing. So this is parabola again, which is shifted by 3/2, but to the left in this case because this is a plus sign. So geometrically, it looks like this on the graph. If this is minus 3 over 2, it will be a parabola which looks like this. And again, crossing with the x-axis is only in one point, and this is the point minus 3 over 2. Finally, my third example, where, if you remember, we did not have any real solutions, is 3x squared minus 18x plus 30 equals to 0. First we divided by 3, that was easier, minus 6x plus 10 is equal to 0. This is x minus 3 squared. Now that would be 9, right? So I have to minus 9 and plus 10 is equal to 0. So this is minus 1. Plus 1. Okay, let's draw the graph. Again, we have the original location of our parabola. Shift it first to the right by 3. That's my list one. But now we have to move it up by 1. So the whole graph will look like this. So this particular parabola, as you see, has no crossings with an x-axis, and that means there are no real solutions. Well, that basically concludes all 3 examples which I wanted to talk about. So let me just summarize very briefly. What's most important in all of these cases was the illustration that you don't really have to remember relatively complex formula for quadratic equation, for solutions to quadratic equation. If you have any quadratic equation, your purpose is to bring it to this form, from which you can obviously very easily conclude that x minus a absolute value is equal to square root of b, which does have real solutions if b is not negative. So x minus a is equal to square root of b, or minus x minus a is equal to square root of b. Or if you wish, I can multiply by minus 1 both parts and have minus here. Or if you wish to do it even more shortly, that's how sometimes it's expressed. Both solutions are expressed in one formula, but using plus minus, from which obviously we have x is equal to a plus minus square root of b by adding a to both sides. So this is a solution if you transform your equation into this format, then this is the obvious solution. And that's probably the most important part which you have to remember from these exercises. Just simplify your equation to this form, and then the solution will be very natural and easy. And from the graphical representation, again, remember that parabola is supposed to cross the x-axis in either 2 points, then there are 2 solutions, that's when the b is positive. 1 point if b is equal to 0, and that would be the point x is equal to a solution, and one and only. And then there are no solutions if b is negative, because the square of the real number cannot be negative. There are no x's. Well, that's it for today. Good luck. And don't forget, check the unizor.com, where there are many other lectures and problems and exercises available. Thank you very much.